hiya, 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 hiya.
Look at a real spring and mass system. So what do I mean by a real spring and mass system? Well, we previously considered a simple spring and then we attached a mass at the end. And in our approximation, we put all the mass kind of just at the end of the spring, but the spring itself had negligible mass. So today we're going to extend this. We're actually going to include the mass of the spring in the calculation. So it's pretty exciting. This is not a problem you typically find in undergraduate textbooks, but it's certainly at the right level. Even though we're adding the mass of the spring, we're still going to assume that the force of the spring is linear, and the force of the spring onto the mass is given by Hooke's law. So the level of difficulty of this problem, I would say, would be first or second year undergraduate level. Probably something involving physics of calculus, and I think it would be slightly above AP physics level. Okay, so let's get started. Okay, before we add the mass of the spring, I want to first consider all of the energy in a system with a massless spring, and all the mass is simply attached at the end of the spring. Okay, for this system here, we're going to have some spring potential energy, which I write as U, and that there simply equals to 1/2 spring constant and the displacement squared. Once the block begins to move, there will also be some kinetic energy. And the kinetic energy, if we're only considering the mass at the end of the spring, is 1/2 mv squared. Okay, so if you evaluate the total energy of the system, E total, at any point is simply equal to the spring potential energy plus the kinetic energy. Okay, if I just simply substitute everything into this equation, I get the 1/2 kx squared. And now I have plus 1/2 mv squared for the kinetic energy. Well, let's try to rewrite this one more time. Okay, 1/2 mv squared. And that's the total energy of the system. Now in this particular system, this total energy is also a constant value. Let me just write that as a constant. Constant. So now what I'm going to do is, I want to get to an equation of motion, and what I'm going to do is differentiate this with respect to time. Notice if I differentiate the constant on the right-hand side, I'm simply going to get everything is going to be equal to 0. Because taking the derivative of a constant equals to 0. If I take the derivative of the spring potential energy with respect to time, I'm left with 1/2 spring constant still there, and this term becomes 2x dx over dt. Okay, and the next term is the kinetic energy term, and here I get 1/2 m 2v and dv over dt. Okay, notice I can cancel some of the terms. There's 2's everywhere in the numerator and the denominator, so I can get rid of those. And I can make some substitutions. In this first term I have dx over dt. Well, that's simply the velocity. Okay, so let me just start grouping some of these terms together. The 2's cancel out in the first term. The x remains, and dx over dt I replace with the velocity. And now plus, in the second term for the kinetic energy, or the derivative of the kinetic energy with respect to time, again the 2's cancel out. The mass is still there. I have the velocity, and the derivative of the velocity with respect to time is simply the acceleration of the system. And that has to be equal to 0. Okay, notice I have the velocity in all of the terms. I can factor that out. What am I left with? I'm left with kx plus ma has to be equal to 0. Okay. One solution for this particular equation is that everything in the bracket here should be equal to 0. So that means that ma plus kx is equal to 0. Now if you bring kx to the other side, you're going to be left with ma equals to negative kx. Now this this equation should look familiar to you. This is exactly the result we would have if we looked at all the forces acting on the mass, as I showed in a previous video. So at the end, if you want to get a solution to this, I can write the acceleration equals to minus k divided by the mass of the block times the displacement. This is our equation of motion, and the solution is simply a function that looks like this: x equals to a cos omega t plus some angle. Again, if you substitute this solution inside this equation of motion, you get that this is going to be a solution to this differential equation as long as the angular frequency omega is given by the square root of k over m, where m is the mass of the block attached to the spring. So you notice this equation for the angular frequency, there's a problem when the mass of the spring, or the mass at the end of the spring, tends towards 0. When there is no mass here, this equation doesn't work very well. It would say that the angular frequency tends toward a very, very large number, and in the limit where there is no mass, you would get that the angular frequency would tend toward infinity. So that doesn't make a lot of sense. So what we have to do now, and what I want to do now, is proceed using a similar approach where I'm going to use energy, and I'm going to try to find what additional contribution we have to the energy when I include the mass of the spring. Okay, so let's try to do that. Okay, so I now want to include the mass of the spring that I'm going to call m subscript s. Now we want to look at all of the energy terms again in the spring mass system, except now I want to include the mass of the spring. And the mass of the spring here is ms. Could be bigger, it could be smaller than the mass attached at the end of the spring. So the first question I have is, does the spring potential energy of the spring change if I include the mass of the spring? So remember what we had for the spring potential energy in the first case. Right? The spring potential energy was always given by the expression 1/2 kx squared, where k is the spring constant and x is the displacement from equilibrium. Notice this term doesn't depend on the mass, right? It has no mass in there. Now, if we include the mass of the spring, this spring potential energy is not going to change. Okay, so when I ask the question, does the spring potential energy change if I include the mass of the spring? The answer is no. The spring potential energy does not depend on the mass of the spring. Okay, it only depends on these two parameters, on the spring constant and on the displacement. Okay? So now let's look at the kinetic energy of the spring if I include the mass of the spring. Next question I have now, we have to consider the total energy of our system, of our spring mass system. And there are two contributions to that energy. Let me just sketch out the spring again. And we have just a mass attached at the end. The mass has a value m. The mass of the spring is given by m subscript s. And we have a spring with the spring constant given by k. Okay, so we know that once this block starts moving, it has kinetic energy. That's straightforward. Whenever a block or anything with a mass moves, there is energy associated to motion, and the value is 1/2 mv squared. Well, what about the spring? What if the spring starts to move? Well, yeah, our spring now has a mass, right? So if I look at a little piece of mass somewhere on the spring, it might not weigh a lot, but you know, this little guy over there is also going to contribute some kinetic energy. which I can probably write as 1/2 whatever the mass of that segment is, and times the velocity of that segment. I can do that for every single kind of chunk of spring that I have, right? This little piece of spring is also going to move, and it might not move at the same velocity as this end over here, but this one will also have a contribution to kinetic energy. Okay? And its contribution, again, it's a mass that moves, therefore its contribution will be its mass times its velocity squared, and 1/2 in the front of that. Okay, so now what we're going to do is we have to include all of the contributions. We have to consider every single mass in the spring and how each one of them move. And we have to add all of their contributions together to get the total kinetic energy of the spring itself. And to that, we have to add the kinetic energy of the mass that's attached at the end of the spring. So at the end, we're going to be left with two terms. Okay, we're going to be left with, let me just write this out like this. The total kinetic energy at the end is going to be equal to 1/2 mv squared. That's the contribution from the block attached at the end of the spring, and plus the kinetic energy of the spring. So in what follows, we're going to try to calculate what the kinetic energy of the spring is. Okay, so let's try to see how we go about to calculate that. Okay, I now want to calculate the kinetic energy of the spring. I'm going to use 3 different methods. The first 2 is basically a proof by exhaustion. What I'm going to first do is I'm going to split the spring down, break the spring up into 4 equal segments, and I'm going to calculate the total kinetic energy of those 4 segments. Then I'm going to take a limit where the number of segments tends toward infinity, and I'll calculate the spring kinetic energy in that limit. And the last case that I'm going to do, which ends up being the simplest, I'm going to use calculus in order to calculate the total spring kinetic energy by integrating the infinitesimal kinetic energies of every segment of the spring. Okay, so let's start with that. So I first begin by splitting the spring up into 4 segments. I've shown the 4 segments here. They all have equal length. And what I'm going to do is I'm going to assume that all of the mass of each segment is simply positioned right at the end of that spring. So all of the mass for spring number 1 is simply at the end. Okay. All of the mass for spring number 2, I'm going to consider it concentrated at position number 2, and so forth. Okay. All of the mass for spring number 4 is simply at the end of spring number 4. The other assumption that I'm going to make now in the following calculation is I'm going to assume that when the spring stretches, it does so uniformly. Okay. So spring number 1 will stretch the same as spring number 4, the same as spring number 2 and spring number 3. They all stretch by the same amount, and they will all contract by the same amount. Okay? Let's write down the kinetic energy for any one of these 4 segments. I can write the kinetic energy, K, for any one of those segments is simply going to be equal to 1/2 the mass of that segment times the velocity squared. So I need to find 2 things now. I need to find the mass of each segment, and I need to find the velocity of each segment. And again, I've assumed for each one of those segments that all of the mass is simply at the end of the spring. Okay, the first term is the easiest to find. Since the total mass of the spring was given by ms, that means that if I break the spring down into 4 segments, each segment will have a mass of ms divided by 4. Okay, now the other assumption I made was that the spring stretches uniformly. Now what does that mean? That means that if you stretch it out, each spring is going to stretch by the same amount that I've written here as delta x. You notice block number 1 though in that instant is not too far from its equilibrium position. However, if you add all those displacements, look at block number 4. It ends up being very far away from its original position, or its equilibrium position. It ends up being 4 times delta x. Okay. So now, if you look at an instant of time and compare how each block will move, well, in one instant of time, let's consider that the spring compresses a distance of delta x. Well, that means that block number 1 in that interval of time will only move delta x. However, each spring will contract by the same amount, and that means that the total displacement for block number 4 is going to be 4 times delta x. If you look at the total displacement in that interval of time for block number 3, the total displacement is going to be 3 times delta x. Okay? So again, the way you would write this out now, let's just write the speed of block number 4 as the speed v. This is also going to be the same speed as the mass that's attached at the end over here. Okay? If I consider this as v, and I consider some interval of time, delta t. Okay? That interval of time will be the same for all 4 blocks, and that's going to be equal to the displacement divided by the velocity of that block. Okay, so if I can write this expression down for block number 1, during that time interval it only moves a single delta x, and it's going to have some velocity v1. That has to be equal to, and if you look at block number 2 will end up moving a total distance of 2 times delta x, and it's going to have a velocity v2. Block number 3 is going to have a displacement of 3 delta x with a velocity v3. And the last step is 4 delta x, and I'm just going to write its velocity as v and drop the subscript 4. So what you get now is if you combine all of these, you get that the velocity of the ith block is simply equal to the I, and it ends up being a fraction of a fourth of the velocity of the block at the end. And now you can check this equation, right? If v equals to 1, the velocity of block number 1 is 1/4 the velocity of block number 4, because it only traveled one distance delta x in some unit time, whereas block number 4 traveled 4 times that distance in the same amount of time. Okay? So this is the expression we have for the velocity of the block as a function of position. Okay, so now I have an expression for the mass of each one, for each spring, and I know how fast each mass is moving. Okay, so now I just need to combine both of these equations together just to get one expression for the kinetic energy of each individual block. So let's do that on the next page. On the previous page, I had that the kinetic energy of the ith block was 1/2 mi vi squared, and the mass of each segment is simply given by the total mass of the spring divided by 4. And I found that the velocity of block number 1 was 4 times smaller than block number 4. Okay, and the velocity of block number 2 was half of the velocity of block number 4, and so forth. Okay, so now we simply combine all of these together to find one expression for the kinetic energy of the ith segment. Okay, so we have 1/2. I'll substitute the value of the mass of each segment. We have ms divided by 4. And now I have to square this term. So I have I v divided by 4. And I have to square the whole thing. Okay, we could take this out. The 1/2 doesn't change. I get the mass of the spring, which ends up being here. Now I'm going to combine these 4s. I have 1 here, and I'm going to get 2 from this term. So I get 4 cubed on this side. The v squared can come out. That's the velocity of the last block. V squared. And now I'm left with an I squared term. Okay. And that's true for I equals to 1 all the way to 4. Okay. So now to get the total kinetic energy of the spring, when I break the spring down into 4 segments, the total K, well, I simply need to sum up all the contributions from the individual springs. Okay. So I have to add all of these individual contributions. So if you combine all that together now, I have to evaluate. There's a bunch of constant terms I can take out. All of these terms can leave. 4 cube is still there. The velocity square term is still there. And now I need to sum over all the values of I, and I need to sum I squared. So here's my expression for the total kinetic energy. And remember, I here simply goes from 1 to 4, because there's only 4 segments. Okay, so all you're left with is having to evaluate this term here. That you can even just sum it out if you wanted to. So you get ms divided by 4 cube v squared. And this term simply ends up being 1 squared plus 2 squared plus 3 squared plus 4 squared. So you get 16 plus 9 plus 4 plus 1. This whole term in the bracket ends up being 30. So 1/2 ms 4 cube v squared, and everything here ends up being multiplied times 30. Okay, that's the total spring potential energy, spring kinetic energy, total of the spring, when I break the spring down into 4 segments. Okay, so now let's look at this expression a little bit more closely, and let's see what would happen if instead of breaking the spring down into only 4 segments, what if I would break it down into a very, very large number of segments? What would change here? Well, the mass of each segment would be simply the total mass divided by the number of segments, and the velocity of the nth segment would simply be the same expression, except I'd be dividing by the number of segments here. Okay, so let's go to the other page and kind of do that. Okay, so now we want to see what the expression for the spring kinetic energy looks like if instead of breaking the spring down into 4 segments, we break it down into a very large number of segments. So here I rewrote the expression we had for the kinetic energy of the spring when it was 4 segments. Now if we have a very large number of segments n, here's what it looks like. Some terms don't change, right? 1/2 the total mass of the spring, and the velocity of the last segment is given by this. Now this term, instead of having 1 over 4 to the cube, I end up having 1 over n to the cube. And the sum, it's the same thing. I'm still summing over I squared, except now I runs from 1, and instead of terminating at 4, it's going to go all the way to n. Okay. So in order to evaluate this sum, this is simply a finite sum of the squares. And actually, if you just Google that, the sum of the squares, or finite sum of the squares, you'll find that this is kind of a very well-known result. The sum of all the square numbers from 1 to n is simply given by n plus 1, 2n plus 1, all of this divided by 6. Okay? And actually, you can check if n equals to 4, whether this result works. Okay? If n equals to 4, remember we had 30 for that, for this summation. Oops. Let's try that. So if n equals to 4, what is this summation? I would have 4 multiplied by 5. And this term here would be 2 times 4 is 8, plus 1 is 9. And all that divided by 6. Okay, you can factor out some of the terms here. Take 3 out of the 9 and the 6. And I can take the 2 out of 4. Cancel that out. I'm left with 2 times 5 times 3 equals 30. So you can see that this formula certainly works for n equals to 4, and you can also verify at any other number. So now we simply have to substitute this term back into our spring potential energy, and we're left with the final expression. So K of the spring is simply equal to 1/2 the total mass of the spring, velocity squared. Now I have this term in the front that's important. This is an n cubed term. Okay. All that is going to be multiplied by 1/6. And now there's 3 terms, right? I have n plus 1, and 2n plus 1. Okay, now what I'm going to do is I'm going to factor this out. Okay, simplify this term a little bit in this bracket. Try to simplify this expression just a little bit further. Okay, so we have the n cubed term that's there. We still have the 1/6. Now the term in the bracket, I can take one of the ends out. The term in the bracket here ends up being 2n squared plus 3n plus 1. And one final step here. Again, if you multiply this n through each one of the terms, we'll end up getting 1/2 v squared 1/n cubed 1/6, and this will be 2n cubed plus 3n squared plus n. So here's our final expression for the spring potential, for the spring kinetic energy when we break the spring down into n segments. Okay. Now what we want to do though is we want to make n very, very large. What happens when the number of segments is so big and it tends towards infinity? How can we simplify this expression? Well, notice we have a 1/n cubed term here, and if I can multiply that through, what am I going to be left with? Going to be left with, this first term doesn't change, 1/2 mv squared. The 1/6 doesn't change. Okay. If you factor out, or you multiply through by 1/n cubed, you're left with 2 for the first term, plus 3 divided by n for the second term, and plus 1/n squared for the last term in that bracket. So what happens now when n tends toward a very big number? Well, this term here becomes negligible, and this term also becomes negligible because I end up dividing by a big number. And all I'm left with is this first term. So the final expression you end up having for the spring kinetic energy when n tends toward infinity is that kinetic energy of the spring, last equation here, is 1/2 ms v squared times 1/3. Here's our final expression for spring kinetic energy. Okay, so there's simply And it's kind of a simple expression, actually, right? You end up just getting kind of a regular kinetic energy expression that you would have for any individual mass, and you end up just having to multiply that term by a factor of 1 over 3. Okay, so that's the total spring kinetic energy when n is very large. Okay, so when we broke down our spring into a very large number of segments, our spring kinetic energy is 1/2. Just going to put that factor of 1 over 3 inside this mass here. And here's our expression. Okay, so that's pretty simple. Now the next thing you would have to do is, remember what we were hoping to do was to see how the angular frequency changes. We still have a block that's connected to that spring, except the mass of the spring is ms. Spring constant is k. Again, now if you consider the total energy of the system, the total energy of the system will be 1/2 mv squared. That's the contribution from this block, plus 1/2 ms divided by 3v squared. That's the contribution from the mass of the spring, and plus 1/2 kx squared. Oops, let's fix this here. 1/2 kx squared. That there is the total energy of the system. Notice it's very, very similar to what we had on one of the first slides. Actually, what I'm going to do is I'm going to group together the kinetic energy terms. So I've just factored out the 1/2 and the v squared terms, just to make the equations look almost exactly the same as one of the first slides I showed today, where we neglected the mass of the spring. You can see that when we add the mass of the spring, the only change is the contribution over here in this term. But we can just deal with this exactly the same as what we did previously. The first step I did was differentiate this equation with respect to time. And then at the end I had an equation of motion, and then I plugged in a solution for that equation of motion, and I obtained that omega was the square root of k over m. I can repeat all of those steps, but I'm not going to do it here. If you do that, what you're going to end up getting is that the angular frequency of the spring mass system, when I include the mass of the spring, is simply 1/2 square root of k divided by this total effective mass. So it's the mass attached at the end of the spring plus 1/3 the mass of the spring. Here's the expression for the angular frequency of a real spring mass system. Okay. So now you can see I can safely take the limit now if I don't include the mass at the end of the spring. Right? This expression is still going to be well behaved, and the system will still oscillate at some angular frequency. Okay? So now that was kind of a lot of work when you start breaking the spring down into a finite number of segments. Let's try calculating the same thing now using calculus, and it can be done in only a couple lines. Okay, so here's a calculus-based proof. Again, I've got my spring now, and the spring has a total mass given by ms. Again, I'm going to look at one contribution from the spring and one tiny infinitesimal contribution that has a length dy. And I want to find the velocity of one of those terms. And I also want to find the kinetic energy of each contribution. Then at the end, I want to integrate over the total length of the spring to get the total kinetic energy of the spring. Okay, the first thing we're going to notice is the mass is uniformly distributed across the spring. Okay. Therefore, the mass can be written as ms divided by the length and times some distance y, where the distance y is measured from the end of the spring here. So notice when y equals to the length of the spring L, I get the total mass of the spring ms. Okay. If you differentiate this, dm over dy is going to be a constant. All right, this spring has a constant linear density, which equals to the mass of the spring divided by the total length of the spring. Okay, so it's great. The next term I need to figure out is what is the velocity of one individual segment. We saw when we broke the spring down into a number of segments that the speed of block number 1 was smaller than the speed of block number 4. The same is going to be true for this spring here. Again, we're assuming that the spring stretches uniformly, and if I go using the same arguments as I did previously, you'll find that the velocity of some segment y that's a certain distance away from the edge is simply going to be related to the position over the length times the speed of the end, or it would be the speed of the block that's attached to the spring. Okay, so you have to have both of these conditions here. So I know what the mass is of one of these tiny little segments, okay, and I know what the velocity is of any one of those segments that's a distance y away. Notice that the velocity increases with distance away from the edge. So now what you want to do is just plug everything into the kinetic energy. The kinetic energy of the spring, or the little bit of kinetic energy for one tiny segment, is simply going to be equal to 1/2 dm and the velocity of that tiny little mass. Okay, so now we're just going to substitute in some of our terms. That tiny little bit of mass is simply going to be equal to, just rearranging that first equation here, dy. And now I got to substitute in the expression for the velocity of that tiny segment of spring. Here you get y over L and v, and you can't forget to square the whole thing. So that is the tiny contribution to the spring kinetic energy from one tiny segment of the spring. At the end, really what you want to do to get the total is you need to integrate each one of these tiny contributions. That's going to give you the total spring kinetic energy. Okay. So in this case, the total spring kinetic energy, if I add all of those contributions, let me factor out all the constant terms first. There's the 1/2, there's ms, there's a velocity squared term there, and here I have L once, and I'm going to have L squared from this term, so at the end I'm left with 1 over L cubed, and I'm left with integrating over the total length of the spring from 0 all the way to L of a function that looks like y squared dy. Okay. Now if you integrate that function, that's very easy to do. You're going to be left with 1 over L cubed, and this term simply becomes y cubed divided by 3, and you're evaluating that from the limits of 0 all the way to L. And that's very clear. When you substitute L into this term, you get an L cubed term, which is going to cancel with this L cubed in the denominator. And the only term you're left with is 1/2 ms v squared multiplied times 1/3. That there is the total spring kinetic energy using a calculus-based approach. See, it's much easier than the previous approach. Only took a few lines of calculations, and we got to the same answer as before. Okay, so there you have it, folks. There was the physics of a realistic spring and mass system where we included the mass of the spring in addition to any mass that was attached at the end of the spring. Okay, if you have any questions, just comment at the bottom of the video.